Okay, there's a snarl of wires down here. You can't see it, but there's just a big mess of wires that I'm very nervous about. Some of these are 110 volts, some of them are 12, some are 5. It's very exciting. I'm Josh Whitman, CEO of Whitman Technological. In the last video, we created the first foot for our Nephele robot, and in this video, we're going to print and assemble the second foot in the Nephele robot. We did a couple modifications to the design and applied that to both feet. Changed out some of the hardware, which meant that we changed out some of our test software, changed out some of our wiring, and all of it for the greater good, I think, which is awesome. Also, this is the first time we've gotten a suggestion from a comment on the internet, and I'm really excited to get some feedback from people that, hey, try doing something a little better, because I'm just goofing around, mostly playing with garbage. So if you've got a good idea, please let me know, and I'd be happy to incorporate it in the design. So previously we were using a stepper controller, and the stepper controller takes pulses from the microcontroller and switches the current on the stepper motor accordingly to rotate the motor. Instead, we're going to use an H-bridge, and it's called an H-bridge because if you picture the motor in the middle and a pair of switches here, so like the positive voltage and the negative voltage, and you have a pair of switches here and another pair of switches here. When these switches are on, the current runs through the motor this direction. And when these switches are on, the current runs through the motor this direction. And so that's why it's called an H-bridge. It has the shape of an H. In the schematic, it actually is just a chip. This is a dual H-bridge, which means it can drive two different motors from this one chip, which is perfect. We'll have our left and right foot both driven by this one chip. And as it was pointed out, the new motors that we're using are going to have less weight and higher torque, higher power compared to the stepper motor. So it's definitely an improvement in the capabilities of our robot. So let's get started by printing the parts that we're going to need. I want to take a second and talk about my software. It's something I love. It's essentially what pays my bills. If you or someone you know has loans or does lending, check out this program. This video is made possible by Moneylender Professional. A labor of love since 2004, Moneylender Professional can seamlessly calculate interest and track payments for virtually every type of loan, lease, or contract. Perfect for single users or teams, 3 loans or 1,000. Generate professional, customizable statements and letters, fully auditable, completely configurable. If you have loans, track them with Moneylender Professional. Okay, wow, man, what a cool program. I'm going to buy 5 copies of it, actually. I could use 5 copies. Now it's time to put the foot together, and we'll see if it works. Here we have all of the parts. Now, we did some redesign work, and this is the one from the previous video with a slight modification. We were working with stepper motors, and we got a question on Reddit why we wanted stepper motors instead of using a gear motor or just a DC brush motor. And the answer was I had stepper motors. I didn't have a good set of gear motors that would work. So But once somebody points out, hey, this is a better way to do it, well, we'd be stupid not to take suggestions, right? So I went and found these were about 15 bucks a piece. They're 550 RPM, 12 volt gear motors. So they're pretty much perfect. I don't even have to change the number of teeth or anything like that for the gear ratios to work out well for these wheels. And the end result is actually the robot will be capable of going just a little bit faster with these gear motors. So I redesigned the brackets a little bit so that it would match up with the bolt pattern on the gear motor instead of the bolt pattern on the stepper motor. And I went ahead and reassembled that first foot using the new brackets, and everything came together really nicely. So we'll start by putting the driven motor. We have a little slot inside here where we can capture a nut. And there we go. So now that bolt connects with that nut, which is great. And then we'll take that and line it up with the flat side of our motor's axle here. Press it on nice and tight, and then we can tighten it down. And now these two are affixed. Looks good. Okay, next we want to, oh no. So I've already made a mistake. So let's take this off. There we go. Okay, because we have to put these brackets on before the gears block those brackets. So okay, now we can put this gear on. We take our 30mm bolts. We just put this whole mess kind of together in one side. This doesn't have to go so tight that it cracks. It just has to be tight enough that it holds everything together well. And the middle one we can tighten up a lot. The front one we don't want to tighten up so much that it rips the layers of the 3D printed part up away from each other, which seems to already be happening. This one print was a little bit deformed. There we go. Probably just broke it. Yeah, I broke it. That's good enough. It's not all the way broken, it's only most of the way broken. That is tightening up, so we don't want to go really any tighter than that. Yeah. Okay. And that's pretty good. It's quieter and there's a lot less friction. And these are just rough. I did no finishing on pretty much any of the parts after they were printed. They're just, I peeled off the brim that it printed, and that's all the work I've done to modify these prior to assembly. That is more than tight enough. Excellent. There's a little bit more friction because that forced the two a little bit closer together, but not at all an unreasonable amount. It still spins very freely. Oh. Whoop. Come on, Mick. Okay. And that is spinning the motor. I am generating a small amount of electricity right now. It's not going anywhere, so it's kind of pointless. Really, I'm just shaking magnetic fields, I guess. That one spins a lot more freely. But that's also had a little bit of a workout. I ran this motor for a while, so it kind of, the gears got a chance to work each other out. There's this kind of like sandy grease you can put in gears that you run the gears with that, and it'll actually wear the gears out just a little bit to help alleviate any kind of artifacts in manufacturing or other incongruencies in the gears to make everything just run smoothly and quietly. And then once it's worked out, you wash all that grease off so it doesn't wear the gears out beyond what's useful. And I've thought about doing something like that with these, but it's plastic. It's going to wear down pretty quickly anyway, so it's not really a priority. And they're already free rolling enough that I'm very happy with it. So there's a snarl of wires underneath me here, and it's all hooked up to a 12-volt power supply, the Arduino, which is powered from USB, and those run into the H-bridge here, which is then wired up to this motor. So it's just going to run on the sinusoid. Whoa. It just goes forwards and backwards. Oh, that tickles. I thought I was getting electrocuted. Here, maybe that's not as loud. Oh boy, does that tickle. You can see the gears running in there. All right, we've got 2 feet for our Nephele project, which is pretty exciting. But I'm a little scared because I have kind of interesting plans for the next chunk of the project. And I don't know if it's going to work very well. So I may end up having to try things a couple of times before I get it right. The next step in the project is going to be the knees. So we're going to connect from what's essentially the ankles here up to the knees. And I want to have a couple of cool facets to the knees. One is that there's going to be casters built into the knees that when standing upright, those casters are retracted into essentially the shin. And when kneeling down, the casters deploy out so that the robot can kneel with its wheels still driving it, but having casters on the front so it's stable on a flat surface. So in situations where you want to power down or low power mode, where constantly balancing and driving the motors back and forth is going to take too much power for something where it's being inactive, or it's just turned off and so it shouldn't be balancing anymore. It'll be able to kneel down on its knees and stay that way until activated again. And I thought about how I wanted to articulate it. I have small stepper motors, and I was going to make gears, and I was thinking I might cast the gears with epoxy. And I found that to be pretty intimidating at the moment. So what we might do is just use these linear actuators that I bought. So these guys can push 100 pounds vertically. They're 12 volts. They're kind of slow moving, but for kneeling down and standing up, it's really not a big deal. I bought like 6 of these. First, I was going to make like a robot arm. Actually, let me get the robot arm. I'll show you the first arm I tried to make. This monstrosity here. Now there's, you can see these universal joints. There's 1, 2, 3, 4, 5 universal joints. Each of those has 4 ball bearings in it. And 1, 2, 3, 4, 5 printed parts. Additionally, there's these variable resistors for position sensing that never quite worked out either. I didn't get too far into it because that design is terrible. There's so much torque at anything other than perpendicular that it was putting a lot of pressure on the printed plastic parts. It didn't work out the way I wanted to. So I have some interesting ideas for how we're going to approach the upper body of the robot when we get further along in the project. So we're going to take those linear actuators, I think, and make those into the thing that causes the knee to extend and retract so that the robot can stand or kneel. And we'll be tackling that in the next video. So I hope you've enjoyed it so far. It's a small step on a very long journey. But I really enjoy the process, and I hope you find it interesting. I'm Josh Whitman with Whitman Technological. I love science, and I hope you do too. Okay, that part is done. There.